Ever wondered how AI systems handle complex tasks without getting bogged down by unnecessary calculations? Let's dive into a breakthrough called Sparse MoA, a smarter way to let AI experts work together efficiently. Traditional AI models use something called mixture of experts, MoE, where specialized experts tackle different parts of a task. But here's the catch. They typically rely on softmax to select the top few experts, ignoring the rest. It's like a competition where only the loudest voices get heard. What if we could make those experts collaborate instead? That's where MoA comes in. Instead of softmax, it uses a sigmoid function, a smooth curve that lets all experts contribute proportionally to their strength. Imagine a team where every member's input matters, not just the most dominant one. This setup fosters cooperation, making the system more adaptable and efficient. But even MoA has a problem. It still calculates every expert's output, even if their contribution is negligible. That's like paying a team of workers for every task, even the ones that don't matter. To fix this, researchers developed Sparse MoA, a system that only activates the experts that truly need to work. Here's the magic. It uses a threshold to decide which experts to engage. Each expert has a score based on the task. If the score exceeds a certain value, they activate, otherwise they're ignored. But here's the clever part. Sparse MoA uses a learnable function to adjust the threshold dynamically per input. Critical parts of a problem get more expert attention, while simpler parts rely on the AI's built-in knowledge. It's like a flexible team that scales up or down depending on the challenge. The results? Sparse MoA outperforms older methods in math and reasoning tasks while using fewer parameters, the settings that define a model. For example, it achieves 81.2% accuracy on math problems with just 22 million parameters, compared to over 100 million in other models. That's like solving a puzzle with a smaller toolbox but better organization. Sparse MoA isn't just faster, it's smarter. By dynamically choosing when and how experts contribute, it bridges the gap between efficiency and performance. And as AI tackles more complex tasks, innovations like this will be key to making systems both powerful and practical. Ever wonder how AI models like chatbots or translation tools make sense of all that text? It's like a team of specialists working together, each expert handling a specific part of the puzzle. Today, we're diving into a study that explores how these experts are activated in a model called Sparse MoA. So what's the big deal? Researchers found that, on average, only about 4.13 experts are active per layer in this model. That might sound small, but it's a key balance between speed and accuracy. Think of it like a kitchen. You don't need all the chefs cooking at once, just the right ones for each dish. But how do they decide which experts to use? The answer lies in router weights, like a traffic system directing input data to the most relevant experts. In one visualization, you can see how these weights shift across layers. Some layers rely heavily on one expert, while others spread the load more evenly. It's like a dynamic team where roles shift based on the task. Here's the kicker. Even with so few experts active at a time, the model still performs well. This suggests Sparse MoA is efficient without sacrificing quality. The numbers in those tables. They're the raw data behind this, showing how different configurations affect performance. But why does this matter? For AI developers, this could mean faster, more scalable models. For us, it's a glimpse into the clever engineering making today's language models so powerful. Next time you chat with an AI, remember, it's not magic, it's a team of experts working behind the scenes. Thanks for watching. If you want to explore how these models are built or see more examples, hit that subscribe button. Stay curious, and we'll see you in the next video. Ever wondered how AI models decide which parts to use when processing information? Let's break down a key concept from this research, the threshold in Sparse MoA. Think of it like a smart traffic system. Each expert in the model is like a specialized lane. If a lane isn't needed for a particular task, the system skips it entirely. A router weight of 0 means that experts' computation is completely bypassed. This keeps the model efficient by avoiding unnecessary work, like not wasting energy on a lane that's rarely used. But here's where things get interesting. How consistent are these decisions across different training runs? The data shows that soft MoA, our traffic system, stays remarkably stable. No matter how we randomize the starting conditions, called random seeds, the expert weights stay reliably similar. It's like having a recipe that always makes the same delicious dish, no matter who's cooking. In contrast, ADA-MoLE's results vary more. This inconsistency could mean less predictable performance. For researchers, stability is key, especially when building models that need to work reliably in real-world scenarios. So Sparse MoA's threshold mechanism isn't just efficient. It's a smart, consistent way to let the model focus on what really matters. Cool, right?